Alrighty guys, so today we are going to be talking about something called periodic trends. And I know the name of this lecture is very long, but we're going to be talking about two different things, and you'll see that on the top of the lecture notes. So the two things we're going to be talking about are electronegativity, okay, and I'm going to abbreviate that EN, so we're going to be talking about that, and we're going to be talking about something called atomic size, okay, and I'm just going to call that size. Okay, so periodic trends is what the topic for today is, and it's basically what the name sounds like. Periodic, so we're going to be talking about the periodic table, and the trends, basically like the patterns on the periodic table. That's going to be what we're going to be discussing today. Alright, so for the warm-up, let's just quickly draw the Lewis structures for these elements. So first we're going to draw one for bromine, and we're also going to do one for bromine's MCI, so we have to figure out what the MCI is. And then we're going to do one for potassium. Okay, so let's start with bromine. So if we look for bromine on the periodic table, you'll notice that bromine is right here. It's in the fourth row. Okay, so to draw the Lewis structure for bromine, we just need to write Br, and we just need to count how many boxes it takes to get to bromine in that row. So 1, 2, and we know that this section right here in the middle, we can always skip that. Okay, so we're going to go 1, 2, and then skip. 3, 4, 5, 6, and bromine is box number 7. That means bromine is going to have 7 dots around it. Okay, so you should have 7 dots. So that means that bromine is going to have 7 valence electrons. Okay. All right, now we're going to talk about bromine's MCI. So bromine's MCI, so this is bromine, but if we do the MCI, we need to figure out if it's going to gain or lose electrons. So let's take a look at this row. In order for bromine to fill up the outside shell, it's only going to need one more, right? Because if I add one electron, it's going to have 8, and the row is going to be complete. So bromine can either gain 1, or it can lose all of these electrons here. So we know from MCIs that it's easier to gain 1 because the number is smaller to just fill up that shell, or to lose everything here. So that means bromine, if I gain 1 electron, I'm gaining something negative. So bromine gains 1 electron, it becomes more negative by 1. So the MCI is going to be Br minus. And we said that there's 7 valence electrons here. So if I gain 1, I'm just going to have to put 8. Okay, so the difference between Br and Br minus is that 1 valence electron in the outside shell. Alright, so we have potassium. So if we're going to do potassium, take a second and try to draw the Lewis structure for potassium if you guys can. Alright, so potassium is right here, the left side of the periodic table, and you're going to notice potassium is the first box in the fourth row. Since it's the first box, that means that potassium's Lewis structure is just going to have 1 valence electron. And I'll abbreviate that VE. Okay, so that's it. Potassium just has 1 because it's box number 1. Alright, for potassium's MCI, we need to figure out if it wants to gain or lose. So if we take a look at potassium, potassium is on the left side. What it can do is it can lose 1 and get rid of this shell, or it can gain all of these. So what do you guys think is easier? Okay, obviously losing 1 is going to be easier. So it's going to be the opposite of Br, because here we're going to want to lose 1 electron. And if potassium gets rid of that electron, it's not going to so regular potassium has 4 shells because it's on the fourth row. But if we lose 1 electron, it's going to become more positive, so it becomes K+. And if I lose this shell, I get 3 shells, because if that 1 electron disappears, that means that shell disappears. And so we just need to figure out how many electrons are in the third shell. Well, we know that there's 1, 2, 3, 4, 5, 6, 7, 8. So that means K+ is going to have 8 valence electrons. Okay, and the reason why is because we lost a shell because we got rid of the only electron in that shell. Alright, so hopefully that was a good review because we're going to be talking a little bit more about valence electrons, shells, and things like that during the lecture today. Alrighty guys, so let's talk about our first periodic trend. So one of the first patterns that we can get from the periodic table is something called electronegativity. It sounds like a super fancy word, but it's very easy to understand. It's basically how tightly does an element hold on to the electron. So how tightly does it hold the electron? So we know from our understanding of atoms that inside the middle of the atom is where the protons are, right? So all the protons are in the middle. Okay, and we know that around the protons, the electrons fly around, right? Okay, and we know that protons are positive, electrons are negative. We also learned that opposites attract, right? If I have a positive charge and a negative charge, they're going to get closer together. So basically what's happening is the protons are pulling the electrons in towards the center, and that's the reason why the electrons don't just like fly out away from the atom. It's because the protons are holding them closely. Okay, now different atoms hold the electrons with a different amount of strength, right? Just like how you might be stronger than me, so you can hold something. You can hold your phone more tightly than I can, right? We can hold different things with a different amount of strength. Same thing with atoms. Every element can hold their electrons with a different amount of strength. Okay, so when we're looking at how tightly they can hold their electrons, how electronegative they are, one thing to keep in mind is the more electronegative something is, the more tightly it holds. Okay, and the less electronegative it is, it's going to hold it a little bit looser. Okay, so more electronegative, you hold it tighter. Less electronegative, you hold it looser. So the way that we determine this is we just go through a process. The first thing that we look at is how many shells there are. Okay, so let's do this example. We're going to figure out which one is more electronegative, sodium or lithium. Okay, and the first thing we want to look at are the shells. So let's look at sodium and lithium. And lithium are right here. Now let's just figure out how many shells they have. So how many shells does sodium have? Okay, sodium is on the third row, right? Because it's on row number 1, 2, 3. Since it's on the third row, sodium has 3 shells. Okay, and lithium is on the second row, so it has 2 shells. Okay, so let's think about this logically. So that means that sodium, if this is the nucleus, it has 3 shells. And the electrons, let's talk about the electrons on the furthest shell, right? And lithium only has 2 shells, so the electron is right here. Now let's just think about this logically. Let's say that you're holding like a pencil, right? Is it easier to hold the pencil if it's very close to you? Or if it's far away, right? If I wanted to steal your pencil, would you be able to protect it and hold on to it if it's close to you? Or if it's far away from you? Okay, obviously, it's easier to hold onto something when it's closer, right? Because it's right there. There's less distance between you and whatever you're trying to hold. Same thing with atoms. If you notice, sodium, the furthest electron is 3 shells away. Whereas lithium, it's only 2 shells away. So lithium is closer to the outside electron. Since it's closer, it can hold the electrons tighter, right? Just like how if you hold something closer to you, you're holding it more tightly, whereas if it's far away, you're holding it more loosely. Okay, so since the electrons are closer to lithium, since it has less shells, the tighter it's holding it, which means that lithium is more electronegative. Okay, so lithium right here is more electronegative. Okay, so the answer to this problem is lithium. And again, it's because it's holding the electrons more closely. Alright, so take a second to figure out how many shells the next problem has. So we have fluorine and beryllium. fluorine and beryllium. So try to figure out, if you need to pause the video, you can. Try to figure out which one holds the electrons more tightly, fluorine or beryllium. All right, so let's take a look at how many shells they have. So we have fluorine right here, and we have beryllium right here. All right, so fluorine has how many shells? It's on the second row, so it has 2 shells. Beryllium, if you notice, also has 2 shells because it's also on the second row. So we did the shells, but this doesn't really help us, right? Because if they have the same number of shells, they're kind of holding it, it seems like, at the same distance. So now we have to move on to the second thing that we look at. The second thing that we look at are the protons. So we have to look at how many protons there are. Alrighty, so when we take a look at the protons, you're going to notice that fluorine has 9 protons because the number on top is 9, and beryllium, the number on top is 4. Okay, so fluorine has 9 protons in the middle. So if I drew, let's say, a small picture of fluorine, I would have 9 protons in the middle, and then I would have the electrons flying around. Whereas with beryllium, I would draw 4 protons in the middle, and I would have the electrons flying around that. So let's just think about this logically. We know that the shells are the same, so they're about the same. The electrons are about the same distance. We learned earlier that the protons pull the electrons closer to the center, right? So if we take a look just at the numbers, right? Which atom do you think has a stronger pull in the middle? Okay, which one has a stronger positive charge? Okay, obviously we would assume that 9 is stronger than 4, right? Because the number is bigger. So the bigger number gives you more protons. Okay, so because fluorine has 9 protons in the middle, right? Think of it like a magnet, right? We have a magnet with a power of 9, and we have a magnet with a power of 4. Which one is going to be able to pull other magnets towards it better? Obviously the stronger magnet, right? So since fluorine, there's more protons in the middle, it's going to be more electronegative than beryllium. And this is because it has the same number of shells. So since the shells are the same, we look at the one with bigger protons or more protons. All right, so again, since fluorine has more protons than beryllium when they have the same number of shells, fluorine is going to be able to pull the electrons in more tightly because it has more protons, a stronger pull in the middle. Alrighty, so if you guys can take a second to try out part C, nitrogen and sulfur, take a look at the shells and then look at the protons. Hopefully that helps you guys figure out which one is more electronegative. So take a second to do that, pause the video. Alright, so hopefully you were able to figure that out on your own. So if we take a look at nitrogen and sulfur, first we want to find them on the periodic table. Nitrogen is right here, and sulfur is right here. So we said the first thing that we want to look for are the shells. So let's figure out how many shells nitrogen has. Nitrogen has 2 shells, and sulfur has 3 shells. So which one do you think is more electronegative? Okay, hopefully you said that nitrogen is more electronegative because it has 2 shells. So if we drew a picture of nitrogen, the electron would be just 2 shells away, right? This would be the distance. Whereas if we drew sulfur, the distance would be 3 shells away. And you can just tell just by drawing it that the distance is further. The further away an electron is, the harder it is to hold. And so since nitrogen can hold the electrons more tightly, this one is more electronegative. Alright, so before we move on, I want to show you guys a quick trick that you guys can use on the periodic table to figure out the pattern. So we said we're talking about trends today. So the trend for electronegativity on the periodic table, and you guys might have noticed this already, but when you're doing the problems, you'll see that as you go up on the periodic table, and you go to the right, they get more electronegative. Okay, so as you go up on the periodic table and as you go right, they get more electronegative. That's the pattern. So as you go up, the reason why that happens is because there's less shells. If there's less shells, right, the distance is getting smaller and smaller and smaller, the atoms are able to hold the electrons more tightly. And as you go right on the periodic table, there are more protons. So as you go to the right of the periodic table, the magnets in the middle become stronger, so they can hold the electrons more tightly. Okay, so that's an easy way to just answer some questions really quickly. So if I asked you to compare, hey, which one is more electronegative, phosphorus or yttrium? Okay, obviously you can just use the pattern and you say, hey, phosphorus is more to the top and to the right, so phosphorus is going to be more electronegative. That's an easy way to just answer the questions. Okay, but make sure you guys still know this method right here, because this will still help you explain your answer, and also it'll help you with more complex problems like the one we're going to do in just a second. But just remember, as a general rule of thumb, as you go up and to the right on the periodic table, they're going to get more electronegative. They're going to hold the electrons more tightly. Okay? All right, so let's do one more example, a little bit more complicated one, and then we will move on to, or actually two more examples, and then we'll move on to the next trend. So if you guys can, take a second, feel free to pause the video, and then you guys can try these problems out on your own. If not, I'm going to go through it step by step. Okay, so we said earlier the pattern is as you go up and to the right, they become more electronegative. Okay, so we're going to use that pattern, because why do more work when we can just use the pattern, right? So let's take a look at Fe. We're just got to find these elements. Fe is right here in the middle. O is right here on the top right. Cl is right here. And Br is right here. Okay, so I boxed our elements, and so hopefully that'll help you guys. Okay, so we're going to start from the least electronegative, and then we're going to go to the most electronegative. Okay, so let's put these in order. So let's start with the least electronegative. We said that the pattern is as you go up and you go to the right, they get more electronegative. So if we look at the bottom left of the atoms that we took note of, you'll see that Fe, right, it's the least, it's the most to the bottom, and it's the least to the right. So that means Fe is the least electronegative. So we're good with Fe. Fe is the least electronegative. Okay, and as we move to the right and as we move up, you're going to see, hey, Br is on the same row as Fe. The only difference is it has more protons. So the magnet in the middle is stronger. So that means that Br is the next one. So it's a little bit greater than Fe in terms of electronegativity. And we're done with Br. All right, so when we take a look at this, this is kind of a weird situation, right? Because they're kind of diagonal from each other, oxygen and chlorine. So which one is more important, going up or going to the right, right? Because O is higher on the periodic table, but chlorine is more to the right. So now we have to look at the things that we learned. So first we have to look at the shells, and then we have to look at the protons. So let's look at the shells. How many shells does O have? O is on the second row, so it has 2 shells. Whereas chlorine is on the third row, so it has 3 shells. That means that O is going to be more electronegative than chlorine. So the order will be this right here, FeBrClO. And the reason why is because of the shells. Remember, if O has 2 shells, the distance is only this much. But if Cl has 3 shells, the distance is further. So that means it's harder to hold the electrons. And so this will be our answer right here. Okay, so we're going to have to use the pattern. We can use the pattern because it's very helpful to use, but we also want to use the order that we learned first, the shells and the protons, because it'll help us kind of figure out the trickier ones, like when they're diagonal to each other, right next to each other. Okay, so if that helped, take a second to try out the next problem on your own. If not, that's totally fine. I'm going to go over it, but if you want to try it on your own, please stop the video, pause the video, and you can try that out. Okay, so take a second to look for the atoms on the periodic table. We have Y, it's my favorite element to say, yttrium, and then we have phosphorus, P. We also have nitrogen. We have chlorine again, and we have fluorine. Okay, so we want to start from the least electronegative, and then we want to go to the most electronegative. Alright, so let's look at the pattern. If we go up and to the right, it's more electronegative. So let's start with the least electronegative. Okay, unfortunately, my favorite, yttrium, is the least because it's to the bottom left. Okay, since it's on the bottom left, it's the least. It cannot hold the electrons very well compared to these ones right here. Okay, and then as we go up and we go to the right, we run into phosphorus. Phosphorus is the next one that's on the bottom left. So phosphorus is next. It's the second least electronegative. Okay, and then we have to move to the top right, and you're going to notice there's one right on top. We have nitrogen on top, and we have Cl on the bottom. So let's for these last three, let's look at the shells, and then let's look at the protons, okay? So nitrogen and fluorine, they're both in the second row, so that means they both have 2 shells. Okay, Cl is in the third row, so it has 3 shells. And since it has more shells than these two, the electrons are further away. The further away the electrons are, the harder they are to hold. So chlorine is going to be next because it has more shells. Alright, and then for the last two, we can either do two things. We can look at the protons, or we can just follow the pattern. If we follow the pattern, the one that's on the more top right is going to be more electronegative. So we can easily guess that it's going to be N and F. But you can also look at the protons. Fluorine has more protons. More protons means a stronger magnet, which means that fluorine is more electronegative. And there you go. We have our answer. It'll be YpClN, and F is the most electronegative. Alright, so hopefully that wasn't too bad. That's it for electronegativity, and you'll see problems similar to this on your assignment today. Okay, we have one more trend to go over, and then we'll be done for the day. The second periodic trend or pattern is something called atomic size. Okay, and if you guys notice down here, we're going to be doing some organizing again. So atomic size is basically just how big an atom is, right? Atomic size, size of the atom. Pretty self-explanatory. So we're going to be figuring out how to know if an atom is bigger. Okay, so let's start with beryllium and barium. And again, we're going to start with the shells. So beryllium is up here, and barium is down here. So let's figure out how many shells they have. Beryllium is on the second row, so it has 2 shells. Barium is on the 1, 2, 3, 4, 5, 6th shell, so it has 6 shells. So let's think about this logically. Which one is going to be bigger? The one with 2 shells or barium? Okay, so while you guys think, I'm going to draw them just so you guys get a visual. Hopefully it doesn't take you very long to figure this out. 1, 2, 3, 4, 5, 6. So which one looks bigger, guys? So this one should have been pretty easy to guess, right? The more shells there are, the bigger they are. So the bigger one is obviously barium, right? Even if you draw them on a piece of paper, and we know that this isn't like the legit dimensions of it, it's kind of easy to tell that one of them is going to be bigger than the other. All right, the next pair that we're going to look at is phosphorus and sulfur. So if you think you guys can do this one on your own, go ahead and try. Let me give you a hint. We're going to look at the protons again. Okay, so if you guys think you can do it, take a second to try it out. But if not, that's fine. I'm going to go over it. So pause the video if you want to try it on your own. If not, you can just follow along. So if we look for the elements, we have phosphorus and we have sulfur, and they're right next to each other. They're best friends. Okay, so if we take a look at phosphorus and sulfur, let's first look at the shells. Phosphorus has 3 shells, right? Because it's on the 1, 2, 3rd row, so it's going to have 3 shells. Sulfur is also on the 3rd row, so it's going to have 3 shells. So that means that both of them have 3 shells, and they're going to be about the same size, right? Because even if you, oops, not P, even if you just draw them, they're going to have 3 shells, similar size. All right, so next thing we have to look at, we said, are the protons. So the protons are the numbers on top. We have 15 and we have 16. So phosphorus has 15 protons and sulfur has 16 protons. So we said earlier that when we have an atom, right, the protons are in the middle. So if we have phosphorus, it has 15 protons in the middle, and we got some electrons around it. And then sulfur, we have 16 protons in the middle, and we have some electrons around it. We said that the protons are kind of like magnets that pull the electrons in. So the question is, which one is going to pull them in more? Okay, a magnet that has the power of 16 or 15? Okay, obviously 16 is a bigger number, so it's going to be stronger. It's going to be a stronger pull. Now, if I pull something in more closely, does it get bigger or smaller? Okay, the stronger the pull from the middle, the smaller it's going to get, right? Because if I'm pulling in the electrons more and more and more and more, you're going to notice it gets smaller and smaller. Whereas if it's not pulling it in that much, it's going to get bigger and bigger. So the bigger atom is going to be the phosphorus because it has less protons. Since there's less protons, it can pull the electrons in less tightly. The more loose it is, the bigger the atom is going to be. So it's kind of like the opposite of electronegativity. Okay, so for this, we also have a pattern, and the pattern is super easy. It's just the opposite of electronegativity. Oh, also, that should not say electronegativity. That should say atomic size. Sorry about the typo, guys. So the pattern for the atomic size on the periodic table is the exact opposite of electronegativity. As you go to the left and as you go down, they get bigger. Okay? And the reason why they get bigger is because as you go to the left, there's less protons. Less protons means a weaker pull from the middle. And as you go down, there are more shells. So that's the pattern. As you go to the left and as you go down, it's going to get bigger. The atoms get bigger. All right. So hopefully that was helpful. Let's do a couple practice and then we will, or I'll let you guys get started on your assignment. Okay, so if you guys think you could just try this on your own, go ahead. But I'm going to go through it step by step. So if you guys want to try it on your own, you can pause the video and skip forward. But I'm going to go over an explanation as we go through the problem. So let's look for the elements. We have Li, we have F, we have my favorite, yttrium, and we have Cs, cesium. Okay, so like we said, as we go to the left and as we go down, they get bigger. So I'm going to write smaller here and bigger and put them in order. So let's start with the smallest. The smallest one would be the one right here, right? The top right. So the smallest one would be F. F would be the smallest, fluorine. And as we go to the left and as we go or as we go to the left, you'll see that we have lithium. So lithium is going to be the next one. And then as we go down, we're going to hit yttrium. And then the biggest one in this group is the one at the very bottom left, and that's going to be cesium. All right, there you go. So that's atomic size. All you need to do is follow the pattern. Okay, so hopefully that was helpful. Try out the last problem on your own if you guys can do it, just because it's good practice for the assignment that you're going to be doing today. So pause the video, try that problem out, but I'm going to go through it step by step if you guys need a little bit more direction. Okay, so we have H, we have O, we have Ra, we have Br, and we have Au. Where are you? There you are. Okay, so these elements are kind of all over the place. So typically, we want to start with the top right because the top right has the smallest ones and the bottom left has the bigger ones. Now for this problem, let's start with the biggest one. Okay, so we'll kind of go reverse just so we can do it both ways. So which one is the biggest? Okay, the bottom left. The bottom left is Ra. Radium is the biggest. Ra is the biggest. Okay, and as we go up and as we go to the right, they get smaller, and we notice that we have gold. So gold is the next biggest. So it's just a little bit smaller than Ra. And as we go up on the periodic table and as we go left, you're going to notice that we have Br. Okay, so Br is going to be our next one. Okay, so I know that this part might be a little bit confusing because we have hydrogen that's all the way on the top left, but oxygen, which is all the way on the top right, but hydrogen is still higher, right? So what's more important, how high they are or, how far to the right they are? So now let's look at the pattern that we said earlier. First, let's look at the shells, then let's look at the protons. Okay, because this will help us understand it a little better. So hydrogen, how many shells does it have? It's in the first row, so it has one shell. Oxygen is on the second row, so it has two shells. So let's just think to ourselves, which one is going to be bigger? Hydrogen, which has one shell, or oxygen that has two shells? Okay, hopefully you said that oxygen is going to be bigger than hydrogen because of the shells. So the next one is oxygen, and the smallest one is hydrogen, even though hydrogen is on the top left. And this will be our answer. Alrighty guys, so hopefully that was helpful. That's going to be the periodic trends that we talked about, electronegativity and atomic size. I'm on the Zoom call right now if you guys need any help. But yeah, good luck with your assignment, and we'll see you guys next time.